And basic probability and statistics is now in session again. Yes, it's the math professor. Hello, statistics fans, and welcome to today's class, May the 4th, 2020. Perhaps this would be a good time to remind you, next week is finals week. I am planning on having the final on Wiley Plus, which will obviously mean that you will have to continue pursuing what you have done so far. If you are having difficulty, you need to contact me by email. Okay, well, I guess that's it for class announcements. There's just not much going on around here. All right. And we're almost there. Okay, I spent a few minutes this morning expanding the slideshow presentation because it does not have as much in the it does not have as much about the chi-squared distribution as I would like. All right, so let's jump ahead till we get to chi-squared, since we've already gone through all of this stuff here before. There we go. All right. So the chi-squared distribution is about finding the variance or the standard deviation of our sample or our population. With the chi-squared distribution, we can create confidence intervals in the way that we did with the standard normal distribution, the z distribution, or the t distribution. All right, so let's plunge boldly into that. Let x1, x2, dot, 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 up to xn be a random sample from a normal distribution with mean mu. Okay, so we know that it is a normal distribution. And our variance, sigma squared. Let sample variance, s squared, be the sample variance. Then the random variable chi squared equals the quantity n minus 1 times sample variance divided by sigma squared. It has a chi-square, and this is the more usual symbol for a chi-squared distribution with n minus 1 degrees of freedom. All right, so last week with the t distribution, we learned about having degrees of freedom associated with our distributions. This week, we're just going to extend that a bit. All right, next slide. So, getting the confidence interval on the variance and the standard deviation. If S squared is the sample variance from a random sample of n observations from a normal distribution with unknown variance, sigma squared, then a 100 times the quantity 1 minus alpha percent confidence interval on sigma squared, or the variance, is the quantity n minus 1 times the sample variance divided by chi-squared of alpha divided by 2 with n minus 1 degrees of freedom is less than or equal to sigma squared, our variance, less than or equal to the quantity n minus 1 times s raised to the second, our sample variance, divided by chi-squared of 1 minus alpha divided by 2 with n minus 1 degrees of freedom. That is where our chi-squared of alpha divided by 2 with n minus 1 degrees of freedom and chi-squared of 1 minus alpha divided by 2 with n minus 1 degrees of freedom are the upper and lower 100 times alpha divided by 2 percentage points of the chi-squared distribution with n minus 1 degrees of freedom, respectively, and possibly respectfully. Ah, bloody hell. I'm already getting dry. I need a hard candy. All right. Now, a confidence interval for the standard deviation, sigma, has lower and upper limits that are square roots of the corresponding limits in the equation 8-9. All right, so the last slide was the equation 8-9. So, the square root quantity of the quantity n minus 1 times sample variance divided by chi-squared of alpha divided by 2 with n minus 1 degrees of freedom is less than or equal to sigma, our standard deviation, less than or equal to the square root quantity of the quantity n minus 1 times sample variance divided by the chi-squared 1 minus alpha divided by 2 and n minus 1 degrees of freedom. Okay, man. Now, for one-sided, we have either the square root quantity of the quantity n minus 1 times sample variance divided by chi-squared alpha with n minus 1 degrees of freedom, less than sigma, our standard deviation, or sigma, our standard deviation, is less than or equal to the square root quantity of the quantity n minus 1 times sample variance divided by chi-squared of 1 minus alpha with n minus 1 degrees of freedom. Ooh, bushel. All right, so perhaps I should have put that last slide that I added in after this one. The 100 times the quantity 1 minus alpha percent, lower and upper confidence bounds on variance are the quantity n minus 1 times sample variance divided by chi-squared alpha with n minus 1 degrees of freedom, less than or equal to variance. Now, the only difference of this from the last slide is this is not a square root quantity, and this is still variance instead of standard deviation. And population variance is less than or equal to the quantity n minus 1 times sample variance divided by chi-squared of 1 minus alpha and n minus 1 degrees of freedom. Okay, that may seem a bit overwhelming at the moment, but we're going to go through and work through these problems and see how that works out. And next, okay, well, we'll go ahead and talk about this for a second. They give us example 8.7. This should be in your book. And it's about detergent filling. Now, this is why variance is important. If we have a machine like this that automatically fills a bottle, we want it to be within some strict limits of how much it fills, or we're going to get detergent all over the floor. And I hate when that happens. Then there's a lot of pratfalls and other clowning around. No good. All right, so a 95% upper confidence bound is found from equation 8-10 as follows. Our population variance is less than or equal to the quantity n minus 1 times sample variance divided by chi-squared of 0.95, comma, and our degrees of freedom is 19. All right, so why is that? Because the sample was 20 bottles. Obviously, 20 minus 1 is 19. Our sample variance, S squared, is 0.0153 squared. And we assume fill volume is normal, and we're computing a 95% upper confidence bound. Ugh. Now, why the upper confidence bound? Why not the lower confidence bound? In this case, the upper confidence bound is more important. If we underfill a little, that's not too serious. If we overfill, again, we get detergent on the floor, it's all over the machines, cats and dogs living together in sin. Oh, wait, no, that doesn't happen. All right, so I went through this equation with you already. So then our population variance is less than or equal to 20, our sample size, minus 1, times 0.0153 divided by 10.117. How did they get 10.117? We're going to have some demonstrations about that in just a minute. And when you work out the math here, it works out to our variance is less than or equal to 0.0287 fluid ounces squared. A confidence interval on the standard deviation sigma can be obtained by taking the square root of both sides, which results in our standard deviation for the population is less than or equal to 0.17. All right. Death, where's thy sting? All right, well, that's actually everything they have about chi-squared in our slideshow. Even at that, as I said, I added one of the slides to make sure that you could see how a one-sided confidence bound works. All right, so I am going to remove my flash drive because last time it removed itself. Probably my foot accidentally pulled it out. That is one of the problematic elements of using these computers that we have here. But there's no reason for me to go into bitching about that. That won't help anything. All right, so you can see I've got my 5th edition book here because it explicitly has problems in it. And I have my chi-squared table from the textbook, the loose leaf textbook, the 7th edition, that you should all have. Although, of course, I recognize that you may not. All right, so let's start with problem 8. Dash 4-2, which from again the 5th edition. All right, 8-42. Determine the values of the following percentiles. And the first one is chi-squared of 0.05 with an n-1 or degrees of freedom of 10. Okay, an excellent question. Now, first of all, let's stop and think for a minute. 0.05, well, it actually doesn't matter if that's our alpha and it's a 95% lower confidence bound, or if it's alpha divided by 2 for a 90% confidence interval that's two-sided, right? The numbers remain the same. Only, all right, so first of all, let's look at our chi-squared table. Across the top, we have alpha, right? And that can be alpha or alpha divided by 2 or 1 minus alpha or 1 minus alpha divided by 2, right? These numbers over here are obviously 1 minus alpha, the 0.995, 0.990, 0.975, 0.950, or 0.900. Those are obviously all either 1 minus alpha or 1 minus alpha divided by 2. The 0.500 is actually needed for something we're not even going to go into in this class. You'll get more about that in inferential statistics. And then should have thought of doing this before. Our alphas or alpha divided by 2's over here, 0.100, 0.050, 0.025, 0.010, or 0.005. Okay, so you can see already that they are going to match up with the values for alpha given on the other side, right? Now, even though on your table it says their values for alpha, they can also be the values for alpha divided by 2. All right, coming down our left side, you'll notice once again we've got new funny looking V for our degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 20, and it goes by ones all the way to 30, and then it starts jumping 40, 50, 60, 70, 80, 100. Okay. So, just to remind you, we are looking for chi-squared of 0.05 with 10 degrees of freedom, right? So that meant it was a sample size of 11. All right, well, 0.050 is right here, right? Obviously, that's the same number, and we're looking for 10. So I put another piece of paper across here at the 10 row, right? I follow that to the corner, so my chi-squared number in this case is 18.31. Quick. write that down. All right, so our next number is chi-squared of 0.025 with degrees of freedom of 15. All right. So, once again, we put our chi-squared table in place, and I look for my 0.025 column, and I've got that here, and I'm looking for a degrees of freedom of 15. Well, I've got that right here. Right? Once again, I follow it to the corner, and I've got 27.49. Cool beans. All right, 27.49. I have to remember that long enough to get back to my original paper. All right, so you can see it's really not too big a deal to figure out what we are looking for on our chi-squared table if we keep our heads about us when all of others are losing theirs, as Kipling said. Okay, so let's do the next one. So it's chi-squared, my papers are in the way, of 0.01 with 12 degrees of freedom. All right, well, 0.01 is actually the same as 0.010, and we're looking, so I put my paper so that it's excluding everything to the right, and then I put my other paper at the 12 row. All right, so following that over, I get 26.22 is my chi-squared number in this situation. So 26.22, let me quickly write that down. All right, our next chi-squared number is 0.950. It just says 0.95 in the book, but what the hell. And degrees of freedom of 20. All right. Once again, we go to our faithful chi-squared table. I'm going to move it up a bit here. One thing I want you to notice, you'll notice that the chi-squared distribution doesn't have a bell curve like the other normal distributions. It has instead what I think of more as an elephant under a sheet shape. So, anyway, there you go. All right. Now I've forgotten. Oh yes, 0.950 comes back to me now. Like the hot kiss at the end of a wet fist. All right, so here's my 0.950 column. And I look then for my 20 degrees of freedom. Okay? Put my sheet of paper under that. I follow it over. 1.10.85. Bloody hell, rough weekend. So 10.85 is our chi-squared number under these circumstances. All right, and what is our next value that we need? We need chi-squared of 0.990 with 18 degrees of freedom. Man, I wrote that close to the last one. All right, easy peasy, lemon squeezy. So I come back here. Once again, I'm using my 2 pieces of paper situation. So I want 0.990, and I put my piece of paper to exclude everything to the right of that. And 18 degrees of freedom, and I put my piece of paper just below the 18 row, and I find 7.01 as my number. All right, so let's go ahead and do the next one. I'm going to give myself a little bit more room here, which is 0.995, and that has 16 degrees of freedom. Freedom! Okay, sorry, I go a little crazy here making these videos by myself. All right, so 0.995. Well, that's our very, very first column here. And we're looking for 16, which is right here. So you can see it's 5.14. Or I hope you can see it. Maybe you're looking at this on your iPhone and saying, What the hell is that bald guy on about? All right, so 5.14. Okay. So for our last problem in lookup, it is chi-squared of 0.005 with, 25 degrees of freedom. All right, in this case, I'm going to push this way up here. All right, so 0.005. Well, really, I don't need my right sheet of paper. It's the last column. Then, here I've got the 25th row, and I go over here to where my two pieces of paper meet, 46.93. Okay, 46.93. Man, that's a big one. All right, so you can see when you're getting started, go ahead and use my two pieces of paper method of looking up. Okay, it's a lot more reliable than just sticking your finger in the book, because you may be in the wrong column, you may be in the wrong row, right? As you get better, of course, you can do that. I'm not trying to save paper. I'm trying to save time in having to scan all these things and post them to Moodle. All right, so our problem 843, part A. Well, I should read the setup first. Determine the chi-squared percentile that is required to construct each of the following confidence intervals. So a confidence level of 95% with degrees of freedom equal to 24, but we want one-sided upper. All right, so one-sided upper means that it is chi-squared of 1 minus alpha and n minus 1 degrees of freedom. So that is chi-squared of 1 minus, so 95% confidence interval means that alpha is equal to 0.05. So 1 minus 0.05, and they just say degrees of freedom are 24, which obviously makes the sample size 25. I mean, come on, guys. All right, and of course I could go ahead and say chi squared of 0.950 and 24 degrees of freedom. All right, well, with that, let's go up a bit so that 24 is well on there. All right, so 0.950 is this column here. 24, all I do is come down till I get to the 24 row, and that number is 13.85. Okay, 13.85, carry on with that. So chi squared of 0.950, 24 degrees of freedom, 13.85. Part A is solved. All right. All right, so B they want a 99% confidence interval with 9 degrees of freedom and for it to be one-sided lower. All right, so that means that it is chi squared of 1 minus alpha with n minus 1 degrees of freedom. That is going to be equal, in this case, because it's a 99% confidence interval, that means that there's 0.01 alpha. So chi squared of 1 minus 0.01. We already know our degrees of freedom is 9. That makes it chi squared of 0.990 with 9 degrees of freedom. And our chi-square of 0.0990 with 9 degrees of freedom is just 3 pieces of paper away from being shown. All right, so here is our table. I go to the 0.990 column, and I exclude everything to the right. And then I go to 9, and I get 2.09 is our chi-squared number. All right, so for part C, they want a 90% confidence interval with a degrees of freedom equal to 19, and they want that to be two-sided. Two sides, no weighting. All right, easy enough. In this case, we start with our chi-squared of, now, what is, well, let's do the 1 minus alpha, because that'll help. 1 minus alpha divided by 2 with n minus 1 degrees of freedom. All right, so that is going to be equal to chi-squared of 1 minus, now, for 90%, that means that alpha equals 0.10, which means that alpha divided by 2 is 0.05. 0.05, and we already know it's 19 degrees of freedom. That means that chi squared of 0.95 with 19 degrees of freedom is what we're looking for. So chi squared of 0.95 with 19 degrees of freedom equals what does it equal? Well, I don't know off the top of my head. All right, but let's stop and think for a moment about, well, you know what? Let's just go ahead and look it up. What the heck? Whose ox will be gored, I ask you? All right. So 0.950, I find the right column here. Then I'm looking for 19, which is right here. Okay, so I've got my column, I've got my row, 0.12. So 10.12 10.12 is my chi-squared number for 0.950 and 19. So 10.12. Now, it's going to be easier for our chi-squared of alpha divided by 2, 0.050, and 19 degrees of freedom. Okay, I carefully, all right. So first I find the 0.50 column, easy enough. Then I find my 19 row. All right, and I see that that is 30.14. Okay, great. All right, so that's two problems where we have either looked up the chi-squared value or figured out our alpha or alpha divided by 2 and worked out what are the chi-squared values that go along with that. Right? Always it's dependent on our particular situation, right? It's not like the standard normal distribution where you look up and you say, oh, okay, well, I want 95% two-sided, that's 1.96, which is a calculation that's used a lot. All right, so here I've blown up. So when we're looking this up, this is either our alpha or our alpha divided by 2. Right, so you've seen that when we're working with a smaller alpha, right, we're actually working down here, and the numbers tend to be much bigger and then get smaller as we go to the 1 minus alpha or the 1 minus alpha divided by 2. All right, so now that we've done that, whew, man, that's well blown up. All right, so let's do another problem. And in this problem, problem 8-44, we're given a rivet is to be inserted into a hole, and a good place for a rivet that is. A random sample of n equals 15 parts. All right, so n equals 15 is selected, and the hole diameter is measured. The sample standard deviation of the hole diameter measurements is S equals 0.008 millimeters. All right, so our sample standard deviation, 0.008 millimeters. Okay, sorry, my millimeters are a little messed up here. Construct a 99% lower confidence bound for variance. Okay, so 99% lower confidence bound. Now, why would we construct a lower confidence bound for this instead of an upper confidence bound? Because the hole is going to have to be a certain size for the rivets to fit in. All right, but you can see this is a tiny sample standard deviation. All right, so given that, we are again, we're doing a lower confidence bound. So I write down my formula, which is the square root quantity of n minus 1 times sample variance divided by, oh, of course, I'm so terrified of making a mistake, I'm reopening the PowerPoint. All right, divided by chi squared of alpha with n minus 1 degrees of freedom is less than or equal to our standard deviation. But what the problem is asking for is they want the lower confidence bound for variance. So I need to square both these sides. Because I was so full of truth and beauty, I got carried away in having the square root quantity. All right, so let's go ahead and substitute in our numbers here. Well, first of all, our chi squared of alpha, and alpha will be 0.01, with a sample size of 15, means that n minus 1 is 14. And of course I have to do my usual looking up. All right, so 0.01, next to last column, and 14. All right, so I'm making that 29.14. All right, there we go. Now, I can go ahead and substitute in my numbers. So square root squared means that we just get rid of both of those terms. It's n minus 1, or 15 minus 1, times our sample variance. Well, that's just sample standard deviation squared. So 0.008 squared. And that is divided by our chi-squared of 0.010 at 14. All right. Let me move lightly over here to the computer. All right, so, equals left parenthesis, 15 minus 1, right parenthesis, 0.008 raised to the second power, and that is divided by 29.14. Oh, okay. And there you go. Oh my God, this is a small number. All right, so let's go with, oh, wrong direction. More digits. All right, well, more digits isn't helping me as much as I thought. All right, so it is 0.0000307, less than or equal to our population variance. Well, damn it, I call that a pretty small number. So that's a very small variance. So our holes being drilled, probably we won't have many problems with them being too small. However, having worked in the aerospace industry, I can tell you one of the major problems with drilling holes for rivets is not that they're too small, but that they are too large. So, in fact, when you assemble an aircraft, as you are putting rivets in, you end up measuring each hole to make sure it is not too large. And if it is, oh my God, stop the presses. Everything comes to a halt while that's fixed. Okay. So, let's consider the problem of a two-sided interval. As I said, often the problem becomes that the whole is too large, not too small. I know it was one of these directions I wanted to move this. All right. In that case, we are going to be looking at chi squared of 1 minus alpha divided by 2 with n minus 1 degrees of freedom. So that is going to be equal to chi squared of 1 minus 0. All right, so if our earlier, if our confidence interval wants to be at 99% for two-sided, that's 1%. Translating that to a decimal becomes 0.005, and n minus 1, n is 15, so it's 15 minus 1. So that is chi squared of 0.99514. So chi squared of 0.9914, oh, I'm starting to write way too little, is equal to what? Well, of course, we look in the famous table, 0.995 is our very first column, and we're looking for 14. So I'm praying you can see it's 4.07. All right, so 4.07. We also need our chi square of 0.005 with 14 degrees of freedom. All right, and so we put our table in place here. 0.005, it's the last column. Why did I even bother with a piece of paper? And I find my 14 rows, so it's 31.32. Okay, now I can put together my formula as n minus 1 times sample standard deviation divided by chi squared of alpha divided by 2 with n minus 1 degrees of freedom, less than or equal to population variance, less than or equal to n minus 1 times sample standard deviation squared divided by chi squared of 1 minus alpha divided by 2 with n minus 1 degrees of freedom. All right, well, I have all these numbers, so easy peasy lemon squeezy. 15 minus 1 times 0.008 squared divided by 31.32. Oh, all right, sorry about that. Less than or equal to chi-squared, less than or equal to n minus 1, 15 minus 1 times our sample variance, which is the square of our sample standard deviation. Uh-oh, forgot a zero. There you go. And that is divided by our chi alpha divided by 2 with n minus 1 degrees of freedom, and that is 4.07. There will be a brief pause while these numbers are calculated. (15 minus 1) times 0.008 squared, close parenthesis, divided by 31.32. Oh man, another tiny one. And just cheating by transferring the numbers down. All right. All right, so that makes it 0.0000286 less than or equal to variance less than or equal to 0.000201. All right, there you go. Now what happens, though, if we want to get the population standard deviation? Well, in that case, I'm just going to do the square root of everything. All right, so all right, so doing the square root, I get 0.00535, 0.00535, 0.0148. And of course, variance is in, millimeters squared, and standard deviation is in millimeters. Whew. Okay, well, you can see it was quite a tussle, but we have defeated the forces of darkness once more. Now look, guys, when I'm doing these problems, don't just sit on your hands and watch me do them. Get your calculator out and be doing the problems at the same time, and hopefully you even have the PDFs or the sheets that I have been doing these problems on printed out, and you're following along as I do them. All right, how much time have we got? All right, we have enough time for, I'm going to call it a couple more problems. All right, I would like to do one of my favorite problems from this section, 8-46. All right, so the sugar content of the syrup in canned peaches is normally distributed. A random sample of n equals 10 cans, all right, so n equals 10, yields a sample standard deviation of S equals 4.8 milligrams. All right, so our sample standard deviation, 4.8 milligrams. Calculate a 95% two-sided confidence interval for the population standard deviation. All right, so 95% confidence interval, two-sided. There, take that. Now, let's start once more with figuring out how we're what our chi-squared numbers are. Because it's two-sided, we are going to need our chi-squared of 1 minus alpha divided by 2 with n minus 1 degrees of freedom. That is going to be equal to chi-squared of 1 minus 0 point what? Well, it's a 95% confidence interval. That means alpha equals 0.05. We divide that in half, and that is 0.025. N minus 1 is 10 minus 1. So that is equal to chi-squared of 0.975 with 9 degrees of freedom. Dare I put it up on that line? Damn it, I dare. We're going to win through and win all, or we're going to fail gloriously. All right, actually, I don't think it's that severe, but... All right, so here we have our table once again. You'll notice there's a 0.975 column, and we know that it's 10 minus 1 degrees of freedom, and we might call that 9. So 2.70. 2.70. Now we need our chi-squared of 0.025 with 9 degrees of freedom. Once again, we use our faithful all right, so here's our 0.025, and here is our 9 degrees of freedom, and you'll notice our chi-squared number is 19.02. Because I'm going to sleep all night, I'm going to sleep all day. Luckily, I remembered in time not to finish the line, that line from the song. All right, now we have absolutely all numbers we need. So let's start out, even though they're asking for the standard deviation, let's start out by going ahead and calculating our variance. All right, so that is our quantity n minus 1 times our sample variance divided by our chi-squared of 1 minus alpha divided by 2 with n minus 1 degrees of freedom less than or equal to sigma squared, our population variance, less than or equal to the quantity n minus 1 times our sample variance divided by our chi-squared of alpha divided by 2 with n minus 1 degrees of freedom. Okay, well, we have numbers for everything except population variance, so let's just stick those in there. All right, so 10 minus 1 times 4.8 milligrams squared divided by our oh, sorry, I screwed up there. 1 minus alpha divided by 2 on this side, 1 minus alpha divided by 2 on the other side. Oh, what a mistake. I'm so embarrassed. I'm just hoping y'all can make the mental adjustment to cover for my screw up. Okay, so we are there for the lower part of the equation. Now the upper part of the equation, 10 minus 1 times 4.8 milligrams squared, and that is divided by 2.70. All right. Well, a quick flick of the wrist, 10 minus 1 times 4.8 raised to the second power divided by our 19.02 . Okay, yes, I get it. I forgot a parenthesis. Oh, what a grouchy program. All right, so I have the lower half, and then I can quickly do the upper half. Except that I made a mathematical error in my input. Wow. Okay, so my lower boundary is 10.902 milligrams squared less than or equal to variance less than or equal to 76.8. Milligrams squared. Boy, I call that a huge variance, or at least a huge range for the variance. We know that the variance is in there somewhere. But the problem actually asked us to calculate the standard deviation. Well, of course, damn it, we're shooting the moon. So we're going to say that is the square root quantity of n minus 1 times sample variance divided by our chi-squared of alpha divided by 2 with n minus 1 degrees of freedom less than or equal to standard deviation less than or equal to the square root, getting closer to the bottom of the screen than I thought, square root of the quantity n minus 1 times sample variance divided by chi-squared of 1 minus alpha 1 minus alpha divided by 2 with n minus 1 degrees of freedom. All right, well, once again, we have all these numbers. It's not mysterious. So we say that is square root of 10 minus 1 times 4.8 squared. Our chi of alpha divided by 2 with n minus 1 degrees of freedom is 19.02. And of course that is the square root quantity less than or equal to sigma less than or equal to the square root quantity of n minus 1 times sample variance divided by chi-squared of 1 minus alpha divided by 2 with n minus 1, which is 2.70. We've already figured that out. All right, well, I can go ahead and go less than or equal to sigma, less than or equal. And in fact, I can calculate my numbers much faster here because all I'm going to do is add a square root to everything. All right, so our standard deviation is 3.301 milligrams at the lower bound and 8.64 excuse me, that should be 8.764. Okay, I should have increased the size of my Excel as I usually do when I'm showing you guys how to work with Excel. All right, well guys, we've gone way over class time for this. But I hope you enjoyed my presentation as much as I enjoyed giving my presentation to you. And please let me remind you, our current situation is going to be over soon. Please stay safe, stay healthy, and when the fields are white with daisies, we'll meet again.